Welcome to part 4 of this slider puzzle tutorial. We've so far created a texture grid and have worked out how to detect which pieces can be moved. We'll now be working on getting the moving and keyframing done, and then we'll optimise the code to make it mix the puzzle more intelligently. So now we can begin the process for the actual animation. We've found our movable pieces, now we need to work out how to move them. Now what you may have noticed when we printed out this long statement here is that it was finding these two pieces, but obviously that's only kind of one move. It loops through all the pieces and detects these two pieces can be moved, and that's just one move. So we actually need to repeat this code for as many times as we want the puzzle to be mixed. And to do that, we put all this code and we press tab to indent it all, and this is all going to sit within another loop. And actually this is also going to be in the loop, so I can remove these spaces. So it's going to be for J, and again, this is just a random letter, range 0, and it's going to be a new control variable called number of moves. So this is defining how many times our puzzle is going to be mixed. So I'm going to go up to the top and say number of moves. I'm going to say this equals to 25. So it's going to swap puzzle pieces 25 times, which actually isn't that much, but at the minute all that's going to happen is that 25 times it will clear out our list of movable pieces, and because we're not actually moving anything anywhere, it's always going to be the same two pieces that it's found that can be moved. So what we need to do is, still within this inner loop, is to pick a movable piece. And to pick our movable piece, we need to generate a random number. And so I'm going to go right back up to the top and import not only BPY, but from random, so from the random Python module, I'm going to import the rand int, which is used to generate a random integer, and this is basically a command which isn't part of the standard Python, so we're just importing it so we can use it. We've hopefully found all the pieces that can be moved in this current move of the puzzle, so we need to count how many pieces we've found. So number of pieces equals, and then we can use the function len, which stands for length. So it'll find the length, whatever we put inside this. So we're going to put movable pieces, which is our list of movable pieces, and then we're going to take one away. And we're taking one away just because if we found 4 pieces, this len command will say you've got 4 pieces, but when we use it in a second, we're going to need the total number of pieces, which is 4, but minus 1. And that's because, like we've had all through this, computers start counting from 0, which means although the total is going to be 4, the maximum is going to be 0, 1, 2, 3. So now we need to select our moving piece from our list of movable pieces. So moving piece equals movable pieces. So this is our list that we've made, and we're going to access one of these properties. So we could just say access the first property. So like any other list, we can access the items in the list with a number, and we're going to use the random integer function that we imported. So we're going to say rand int, open and close brackets, and it needs a range of numbers to generate a random integer from. So what range do we want to have the random integer in? Well, between 0, which is going to be the first item in the list, and number of pieces. So we need a random number between 0 and 3 if there are 4 items, or 0 and 2 if there are 3 items, and so on. So this is choosing a random item from our list. So now we can actually start moving our pieces in 3D space. So what we need to do is store the location, or the old location, of this empty piece, because we're going to be swapping them round. So we need to store its current location. So I'm going to say old piece x equals moving piece dot location x, and old piece y equals moving piece dot location y. So we've selected a random piece from our movable pieces, and we're going to store its location. And we're then going to insert a keyframe. And to do that, we can say moving piece dot keyframe underscore insert, open and close brackets, and then there's a property called data path, and this specifies the property that you want to keyframe, and we want to keyframe the location. So this keyword here is simply the dot location property here, so we could animate dot rotation Euler or dot scale. We're saying location, and because location is a list made up of multiple items which we've been accessing, we want to animate the first item, which is the x, so we're going to say index equals 0. We're then going to do the same for the y location, which just means this has to be 1. And we're then going to do the same, but for the empty piece. So remember, these pieces are going to be swapping, so they both need keyframes. So I'm just going to copy empty piece and paste it in. So we're storing the location of our moving piece, we're keyframing both our pieces, and then what we need to do is change our frame. So basically, we want to now change this property, which determines where we are in the timeline, and we set this by using bpy.context.scene.frame underscore set, and then open and close brackets. And if you remember how I said we were going to create this, we're starting off with a puzzle that's not mixed, and we're actually mixing it. But in the video, the opposite happens. We watch something that's mixed, and as we move along the timeline and the animation plays, it returns to its unmixed form. So the way we're going to insert keyframes is by starting at the end and working our way back towards the beginning. So what we need to do is determine where the end of our animation is going to be. So it's probably not going to be frame 250. So we're going to change this end frame property, which is scene.frameEnd. And what it's going to equal is the number of moves we've specified, so how many times the puzzle is going to mix, and how many frames we want each move to take. So we actually need a new control variable. So we've said we want the number of sides to be 4, we want the puzzle to be mixed 25 times, and we're now going to say that the number of frames each move should take, well, I'm going to say it should be 4 frames. So to work out how long the animation is going to be, you simply multiply the number of moves by number of frames per move. So the frame end equals number of moves times frames per move. And then what we'll find later is that if we just add 1 on the end, it means that we don't start from 0, but we will see that a bit later. So then we also need to set the current frame. So we know what the maximum end is going to be, but we now need to set the current frame. So bpy.context.scene.frame underscore set, and it's going to be exactly the same, because we are starting from the end of the animation and working our way towards the beginning. So we're setting the maximum to be the end, and that's where we're moving the timeline marker. And then we're going to work our way forwards as we set keyframes. So, back to here where we got to. We've inserted our keyframe, and we now need to move our timeline marker again. So we're going to say frame set should be whatever the current frame is. So bpy.context.scene.frame underscore current, which is this value. So whatever the current frame is, minus frames per move, which is 4 as we set it at the top. So each time this runs, it will move back 4 frames inserting a new keyframe. And now we need to actually move our objects. So we're going to say moving piece.location x equals empty piece.location x. And then we can copy this and do the same for the y. So we've moved the moving piece. It's getting a bit confusing with these names. And now we're going to move the empty piece. So empty piece location x equals, and remember we stored the location where it's got to move to. So that's old piece x. And then we're going to do the same for y. And now it's time to insert our keyframe. So I know we've written quite a lot of code and we haven't actually kind of tested as we've gone. And that's kind of because this is one of the sections where if we don't do it all at once, it'll simply just kind of not work and look a bit weird and you won't be able to really tell much. So we do need to do this whole block all at once. And I have just made one small mistake, and that's the fact that this whole block of code needs to be unindented by one tab space. And that's because it was indented to the point that it would be part of this loop, and it's not meant to be. It's meant to be part of this larger loop, so this J loop, but not part of this I loop. So I've just lined it up to make sure it is only part of this outer loop. So if I bring back the console window, and I'll just run the script again, and we can see we've got something going on now. And if I scroll through the timeline, we can see that our puzzle has not only been mixed, but it's been animated. So essentially, you could just leave it there. You've got a working puzzle. However, there are many things we can do to optimize the way this works. So the first thing we can do is actually an optimization for how it detects moving pieces. This loop we've got here is going to loop through all the pieces in our puzzle. But we know that we can only ever find a maximum of 4 movable pieces. So if by chance we loop through the pieces and the first 4 pieces it selected was this one, this one, this one, and this one, and so they would all be movable pieces, we found a maximum of 4, and we know that we're not going to find any more movable pieces. None of these other ones are going to match. But currently our code is still going to loop through them. So what we can do is add in a small check to say that if the amount of movable pieces is 4, then you don't have to keep on looking for more movable pieces because there aren't going to be any. And we can put this check directly under the point where we add our movable pieces to our list. And then it'll say, have we got to the maximum of 4? If we haven't, it will continue. And if it has, we're going to use a command to stop the loop. So what we can do is say if, and we're going to use the keyword len again to find the length of our list. So we're finding the length of movable pieces. If the length is equal to 4, meaning there are 4 items, and then we can use the keyword break. And break says stop the first loop that you come to. So it'll look outside of this code and it'll say, here's the first for loop, stop looping. So it'll stop looking through all the pieces and continue on and start the keyframe process. Now we won't actually notice much difference in the puzzle, but on a larger puzzle you'll notice a speed increase because basically it's having to do less looping. So again, just run it to make sure it's still working. So there is another problem with the way that this is currently working, and if I scroll through, I'll try and find a place. Yeah, here's a place where it's happening. We see this empty piece, this grey piece, it's swapping and then it's immediately swapping back. And that's because it's obviously out of the 2 available movable pieces, by chance it has selected the same one that it's just swapped with. So it's moving, oh yes, this is a movable piece, and it's moving back. So what we want to try and do is prevent it moving with the piece it has just moved with. And we're probably getting this quite a bit throughout the animation. See, there's another one. It's moving, and by chance it's picking the same one it's just swapped with. And it's happening again there. So what that's doing is basically just wasting moves. It's also not going to look very good. So we can do a check to make sure the current moving piece that it's selected isn't the same as the previous one. So to do that, I'm going to define a new empty variable. So it's just going to be an empty string that I'm resetting at the top of our animation. And this is the code just here where we're selecting a moving piece. So now we want to check that this moving piece isn't the same as the old one. And for this we can use a loop we haven't used before in this code, and that's a while loop. So we're going to say while moving piece is equal to old piece. So while it's the same as the piece from the previous move, and we haven't defined what old piece is going to be yet, we will then basically repeat this code so it can select a new moving piece. And it's going to repeat this. So if by chance it, just at this point, found, yes, these are two movable pieces, it may pick this one and say, oh, well actually, I've just moved that, so I'll try picking another one. And again, by chance, it could pick the same one continuously, because of course we are generating a random number, so it could randomly generate the same one, but it's just going to continue choosing a new piece until it has definitely found a different one. So after it has found the piece, we can then say that the old piece is equal to moving piece. So the first time this runs, the old piece will be blank. So say, does moving piece equal old piece? No, because moving piece won't be blank. And so then it'll say, well, for the next time I move, I will store this current moving piece. So the next time it runs, it will say, does this moving piece equal this previous piece? So if we run this, we should have a far more efficient puzzle now. So we shouldn't see it going back and forth. And you can see it's definitely changing a different piece each time. There's no point where it's going backwards and forwards. And you can very easily see the difference just by disabling these two lines. And you see, there we are, I've got that swap again. And again there. And again there. And there. So this is a very inefficient one. Just adding these lines, it now removes those pointless swaps. So what we'll also see is most of the puzzle is being mixed, but there's still some areas up here that aren't getting moved at all. But you can see at this point in the puzzle, these pieces are just being mixed repeatedly, which is also a bit of a waste. You know, really, it should prioritise these pieces that haven't been moved over pieces that have been moved to try and mix the puzzle a bit quicker. So again, we can create something called priority pieces, which is a way to determine if a piece has been moved before. So to do this, I'm going to move right to the top of the code, and we're going to add a new property for all objects in our scene. And I'm going to do this just after this import, and we're going to say bpy.types.object. So the object is a type. You could have this as a scene and add a new scene property, but we're adding a new property to an object, and I'm going to call this property has moved. So has the piece moved or not? I'm going to say this new property is going to be of type bpy.props, and it's going to be a bool property, which means it's a boolean, which means it's going to be true or false. And I'm going to set the default to false. And you can see all the different types of properties you can have down here in the Python console, bpy.props, and you can see you can have floats, integers, strings. We've chosen a bool. So if I run this, let's select an object, so puzzle1 piece 2, and we'll access it with bpy.data.objects puzzle1 piece 2. And if I use autocomplete again to see all the properties of the object, if we look in this list, we can now see our custom property has been added, has moved. So if we access that property, has underscore moved, we can see it's got that default value that we gave it of false. So that's a way of adding new properties to an object. Now that we've set this property, we need to create a check for this property. And so basically what we need to do is, after our list of movable pieces has been created, we need to run a check on it to see if any of those pieces have been moved before. So I'm going to say for piece in movable pieces, so we can loop through this list, and I'm going to say if piece dot has moved, so this is the property we just created, equals false, and then I'm going to create a new list called priority pieces, and I'm going to append the piece to it. So I do need to create this list. So just above, I can create priority pieces and make it an empty list. So if has moved equals false, then you should add it to our priority pieces, because we want to prioritize pieces that haven't been moved yet. But then this isn't actually doing anything. Alright, so we've got a new list of priority pieces, but we're still choosing down here a random piece from our moving piece list. So this is basically ignoring our priority pieces. Well, we can say if len, so if the length of priority pieces, the list we have just created, is more than 0, which means there is at least one priority piece, there's one piece that hasn't been moved yet, and then I'm going to overwrite our movable pieces list. I'm going to say movable pieces equals priority pieces. So this is saying if there is even one piece that hasn't been moved yet, then remove all the pieces from our movable pieces list and replace them with our priority pieces. If, however, there aren't any priority pieces, because maybe they've all been moved before, then don't adjust this list, and we're just going to use the movable pieces we collected earlier on. One final thing we have to do is that after we've actually selected our moving piece, which is after this while loop, we're now going to set the moving piece .has moved property to true, because this piece has now been moved. So let's run that, and we're not going to see a huge difference. It is generally on the larger puzzles that you see this difference, but basically, where possible, it will move pieces that haven't been moved before, and you can see we're not quite getting that same, there was a time before where this empty piece was kind of going in a circle for a bit because it was just selecting the same pieces, and we're getting far less of that. It's going in a far bigger path this time, and nearly all the pieces, I think, are being moved now. Now, again, that's not going to happen every time, because there are going to be instances where simply all the pieces it finds have been moved before, so it can't prioritize anything. But in general, it does make a big improvement, and it's only a few lines of code to have quite a good improvement. So one of the final things we can do is add in our percentage print function. So percentage print, and this time the name we want it to print out is animation, and this time the total is going to be the number of moves, because that's how many times this code is going to run. It's dependent on the number of moves we've specified, so that's going to be our total. So if we run that, we've now got a percentage for how complete our animation is. And remember, we are resetting our counters here, so the other print commands were using total pieces, because these loops were running dependent on the number of pieces there were, but this loop is running dependent on the number of moves, so that's the total we're going to use. So that is all the code done. Something you can also do now, you can Shift A and add an empty, Control P, and you can now parent your whole grid to this empty and move it round in your scene, and all the animation should still work. So that's a way of moving it around. And if you remember at the beginning, I said you may want to have multiple slider puzzles in your file. And how do you do that? Well, all you have to do is change our name. So you remember our delete function is looking for our previous objects based on that name. But now that I've updated the name, it's no longer looking for puzzle 1, it'll only be looking for puzzle 2 pieces. So we can now run that. We've now got multiple puzzles. And what I have here, this is obviously not a regular shape. It's not a 4x4 grid. This grid was made manually by just duplicating pieces. And so I was able to create a custom shape. And if you adapt the code a bit, so that obviously it doesn't have to create a new grid, then you can actually still have a working puzzle, but using an irregular shape. And you can actually use any shape you want. But as long as there is a 1 tile width to any part of your puzzle, it'll be able to go there, because it still fits within the rules of the algorithm we wrote. And so this way, you can have highly complex shapes and still use a bit of an adapted code. Anyway, that's been quite a long tutorial. I hope you have learned something from this. We went over quite a lot of code, so I imagine you may have to watch some of this back to get the hang of it, and we may have gone over some quite complex parts of the code, particularly when looking at how we're choosing our pieces and our priority pieces and things like that. But as long as you take it in sections, run the code quite a lot to see how new commands update the effect, you should be able to learn something. And because the code is quite long, with many opportunities to go wrong or to miss small parts of code, for this reason I've uploaded this script to GitHub, where you can view and download the finished code. I hope you have found this tutorial useful, and I hope to see you in the next tutorial. Goodbye.